So here we want to find an equation of the tangent line to a curve at a given point. So in the previous video, we simply used the slope of the secant line, and which we find between 2 points and bring it closer and closer to a single point, and we reduce the slope of the secant line to the slope of a tangent line at a single point, because a tangent line touches the curve exactly at 1 point, whereas the secant line touches a curve at 2 points. So we can take that approach, but now that we have a difference quotient from earlier, so the formula for difference quotient is right here, and we're going to make use of the difference quotient to find the slope of the tangent line. So how does this work? Now we have x and x plus h, and if I took the limit h approaching 0, then the point on the right hand side, x2, as h becomes smaller and smaller, it's going to move closer and closer toward x. It is the same concept where we narrowed the slope of the secant line and to a single point. We're going to move the value of h closer and closer to 0, which would bring the point x2 closer to x1, reducing the slope of the secant line to the slope of the tangent line. So instead of doing that computational approach, we're just going to make use of the difference quotient to find that value, which is the slope of the tangent line. So how do we go about doing that? The very first step is to use the difference quotient. I'll just write it as dq. It's given by that formula. Now, keep in mind, you can't simply plug in this formula and apply the limits directly. You would get 0 over 0, you would get an indeterminate form. So be very careful. We have to do some algebra here. So I'm going to start with f of x plus h. So I'm going to replace the x there by x plus h. Make sure you put the parentheses properly. So 4 times x plus h minus 3 times x plus h squared. That is the f of x plus h part, minus 4x minus 3x squared. That is the f of x part. So that is f of x plus h minus f of x. And divide by h. So we have 4x plus 4h minus 3 times FOIL x squared plus 2xh plus h squared. Distribute the negative, minus 4x plus 3x squared divided by h. So I can get rid of the 4x term, and that would leave me with limit h approaching 0, 4h minus 3x squared minus 6xh minus 3h squared plus 3x squared divided by h. So those two terms would go away, leaving us with limit h approaching 0, 4h minus 6xh minus 3h squared. So So what do we have in common in the numerator? We have a h in common, so limit h approaches 0, 4 minus 6x minus 3h squared divided by h. All I did is I pulled the h out, so that would be 3h. Cancel the h. And now we could simply apply the limit. The first term doesn't have h in it, so it will remain as is. The second term doesn't have h in it, so it remains as is. The third term has h in it, so when we apply the limit, it goes away. 3 times 0 is 0, so we end up getting 4 minus 6x. That is the limit h approaching 0 of the difference quotient of f of x. And that is simply the slope of the tangent line. So the given point is 2, minus 4. So we have a point, and at that point we can find the slope of this function. So all we have to do is find m. So how do we find m? We have the slope expressed in terms of 4 minus 6x, because that is the slope of the tangent line. And if we plugged in 2 in that equation, y equals 4x minus 3x squared. We have 8 minus 12, which is negative 4. So this point is simply the point where we're trying to find the equation of the tangent line. So I have an x coordinate there, which is x. So plug in x is equal to 2 in the slope of the tangent line that we derived. So m would simply be equal to 4 minus 6 times 2, which is 4 minus 12. We get minus 8. So if I represent it in point slope form, the point x1, y1 is 2 and negative 4. So y minus y1 is equal to m times x minus x1. So the equation of the tangent line in point slope form is y plus 4 equals negative 8 times x minus 2. So that is the final answer. If you want, you can write it in the slope-intercept form with a little bit of algebraic operations. So here we have y equals square root of x, and we have 1, 1. Let's do the same thing. Limit h approaches 0, the difference quotient. So limit h approaches 0, f of x plus h minus f of x divided by h would simply be the slope of the tangent line. So we have the point already. If we find the slope, then we can put it in the point slope form, and if we can put it in the point slope form, we could write it in the slope intercept form. So let's see. Limit h approaches 0, square root of x plus h minus square root of x divided by h. Now, in the previous video, I did a couple of examples where if you apply the limit directly to this particular difference quotient, you will get 0 over 0, which is an indeterminate form, and obviously that is not the correct answer. So what should we do? we have to rationalize the numerator. So we multiply and divide by the conjugate. The conjugate of the numerator, square root of x plus h minus square root of x, is square root of x plus h plus square root of x. So if I FOIL the numerator by multiplying that term with that term, we will have square root of x plus h squared minus square root of x squared divided by h times square root of x plus h plus square root of x. The root and the square would get cancelled, and we would simply have limit h approaches 0, x plus h minus x divided by h times square root of x plus h plus square root of x. The x's would go away, and we'd simply have limit h approaches 0, h divided by h times square root of x plus h plus square root of x. Now the h goes away there, and we'll simply have 1 over square root of x plus h plus square root of x. When we apply the limit, the first term would become square root of x in the denominator. The second term would also be square root of x. And if I combine the two, I'd simply have 1 over 2 root x. And that simply is the slope of the tangent line in terms of x, which we obtain using the difference quotient. All I have to do is now plug in the point that we have in the problem. That is the correct point corresponding to the function. So if I use that point in the slope of the tangent line, I'll have m equals 1 over 2 times square root of 1, which is 1/2. So I have the slope of the tangent line at 1, 1. And I know the point where I'm looking for the tangent line, which is 1, 1. So if I put it in point slope form, I have y minus 1 equals 1/2 the slope, x minus 1. So that would be the point slope form. Let me just go ahead and convert it to the slope intercept form. So we have y minus 1 equals 1/2 x minus 1/2. Move the 1 to the other side. So y would equal to 1/2 x minus 1/2 plus 1. So y would equal to 1/2 x plus 1/2. And that is the equation of the tangent line at 1, 1 for the function y equals square root of x. So we did difference quotient already, and we found the slope of the tangent line using the difference quotient, which is the benefit of having the difference quotient. Now we're going to do 2 simple examples on difference quotients. There is an interesting behavior that you should have noticed already. If not, in these examples I would mention what that behavior is when we find the difference quotient. So the difference quotient is simply f of x plus h minus f of x divided by h. The function is x squared minus 4, so x plus h squared minus 4 minus x squared minus 4 divided by h. If I FOIL, I have x squared plus 2xh plus h squared minus 4 minus x squared minus 4. I'm leaving it as is for a reason. Now I'm going to go to the FOIL version and I'm going to move that term and that term close to each other and write it this way. X squared minus 4 plus 2xh plus h squared minus x squared minus 4 divided by h. And those two terms will get cancelled and you'd have 2xh plus h squared divided by h. We have the h in common in the numerator, so h times 2x plus h divided by h. The h's would go away. We simply have 2x plus h. Something interesting happened. If you observe carefully, excuse me, f of x is x squared minus 4. And when we found the difference quotient, that x squared minus 4 got cancelled. So it just went away. So if we do everything properly, the original function will disappear when we find the difference quotient. That is a key thing to notice. And we saw it in the previous one. Square root of x disappeared. And here 4x minus 3x squared disappeared. So if we did the algebra correctly, the original function x squared minus 4 will disappear when we find the difference quotient. So the last step, or the last problem, is f of x equals 1 over x plus 1. So the difference quotient is f of x plus h minus f of x divided by h, which is 1 over x plus h plus 1 minus 1 over x plus 1 divided by h. We need to get a common denominator if we have to combine those two together. So the common denominator between x plus h plus 1 and x plus 1 is the product of the two. So I'm going to multiply and divide by x plus 1. And over here, I'm going to multiply and divide by x plus h plus 1. And divide that by h. So now I have a common denominator. So I have x plus 1 minus x plus h plus 1 divided by x plus 1 times x plus h plus 1 divided by h. If you flip and multiply, we'd simply have x plus 1 minus x plus h plus 1 divided by h times x plus 1 times x plus h plus 1. Distribute in the numerator x plus 1 minus x minus h minus 1 divided by h times x plus 1 times x plus h plus 1. The x's would go away, the 1's would go away. We have negative h over h times x plus 1 times x plus h plus 1. The h's would go away. We simply have minus 1 over x plus 1 times x plus h plus 1. Now, just in the last problem, I mentioned that if you did everything properly, the original function is going to disappear and things would just fall in place. But in this problem, it didn't seem like it. 1 over x plus 1 just didn't disappear. It's not obvious. And in the square root of x problem over here, it wasn't obvious. The algebra that we did somehow worked out, and we ended up getting the answer. So typically with algebraic functions or polynomial functions, such as the quadratic, the linear function, a cubic polynomial function, all of those, when you find the difference quotient, the original function would just disappear. So x squared minus 4 here is a second degree polynomial. It is a quadratic function. It is going to disappear. But 1 over x plus 1 is not. It is a rational function, and which is why it is not quite obvious. But if we did some bit of algebra in other ways, perhaps it would become obvious, but we don't have to get into that. So anytime you have a radical function or a rational function, it won't be obvious. The original function, even though it is going to disappear, it is just not going to be obvious. But with polynomial functions, such as x squared minus 4, when you find the difference quotient, the original function will always disappear.